Today we're going to cover lesson 10.1 on Introduction to Vectors. I know we are now just starting this video, but would you take a moment and pause the video, read these two initial paragraphs, and then come back to me. Okay, thanks for taking the time to read that. So in summary, these two paragraphs are just helping you draw a comparison between quantities that are known as scalar and then those type of quantities that actually are called directed quantities that require us to involve magnitude and direction. And one way to represent these new quantities that we call directed quantities is using vectors. And that's what this chapter is going to be all about. So in our bulleted points over here, we see that a vector requires us to know the magnitude and direction of said directed quantity. The definition of magnitude is the length of that vector, the length of a directed line segment, which looks like a ray, if you guys recall from geometry. And direction merely just means the angle between the positive x-axis and the vector. So what that means here is if this was my x and y coordinate axis and we had a vector, this right here, that theta is your directed angle, okay? It is always going to be measured from the positive x-axis and rotating counterclockwise. So that's going to be covered more in 10.2. But let's see what exactly does a vector look like, and let's talk about some properties, okay? So here is our image of a vector. A vector has a tail where the graph begins. The arrow begins, and then you have a head, arrowhead, where the vector will end up ending, okay? So you have a beginning point and ending point. The distance from that beginning to ending point of your vector is called the magnitude. That magnitude is the length of the vector. And we talked about direction. If this was the x and y axis, the angle of this vector is going to be the direction. So let me show you guys something specifically. We'll leave direction for later, but I want to talk about magnitude right now. So I am going to draw a vector in this coordinate plane. It is going to initially start from the origin, and let's say it ended right over here at 3, 4. And that's not a very straight vector, so let's do this again. There we go. All right. So there's my vector. My tail is at 0, 0, okay? And my arrow ends at 3, 4. So I'm going to put some dots here just to provide some visual context of the beginning and end, okay? So if I asked you for the magnitude of this vector, so magnitude means the length, okay? Now, I'm going to talk about this a little bit later in your notes, but let's pretend that we are going to call this vector by the letter U, okay? So the letter U would have an arrow above it so that in math, when we see something like that, we know that that means read it as vector U. Now, if I'm asking you to find the magnitude of vector U, so I'm going to write something down here. Find the magnitude of vector U. That's a little bit tedious. So what mathematicians did was figure out what's an easier way to write this that we can all agree about and use symbols. So instead of writing find the magnitude of vector U, they said, well, let's use a bar with the name of the vector and another bar, and that means this. So I need you guys to understand, if you see something that looks like absolute value bars around the name of a vector, that means I'm asking you to find the magnitude of vector u. I also want you to know that some books like to use 2 bars like this, and that also means magnitude of vector. So either one of those means the same thing. I'm just going to use 1 bar, but I want you to know that 2 bars are also used on either side. Okay, so let's go back to magnitude. I'm asking you to find the magnitude of that vector. So basically, let me erase this word here a second and this right here. What I'm asking you to do is to figure out how long that is. So if I were to just tilt this arrow and use the x-axis as a way of measuring it, I'm going to move it over here. Notice that, oh, the magnitude of my vector is actually 5 units long. So I would say the magnitude of vector u, or did I say it was v? I can't even remember what I used. Let's say I said it was u. Magnitude of my vector u is 5 units long, and I'm done, okay? But is there a way that we can figure out the length of that vector without having to always move this arrow and rotate it so that we can measure it against the x-axis? Absolutely, there is a way. So how are we going to do that? So let's go back to rotating this the way it was, and let me position it back here. So what I'm hoping you are noticing by now is that this vector has an x component to it, and it has a y component to it. Do you notice that? So the x component is a 3 and the y component is a 4. So let us do 3 squared plus 4 squared to get that hypotenuse, right? And that's a 9 plus a 16 equals my hypotenuse squared, which makes 25. And of course, we have to square root both sides to find our hypotenuse length to be a 5. So the magnitude of a vector can be found always by using the Pythagorean theorem. Okay, so let us go to that handout. All right, and before I go back to our note-taking guide, what I want you to know too, and we'll talk about this in 10.2, is that the angle, the directed angle, is always going to be measured from this x-axis, okay? It always has to be measured from this x-axis, and we are going to rotate counterclockwise. So in this sense, wow, in this sense, we would have to figure out what this angle is, and that angle would be your direction, okay? But we're going to just focus on magnitude, right? If you want to figure out the length of your vector, you will apply the Pythagorean theorem. So if you know what A and B are supposed to be the length of the x component, so this is the x component of your vector, or the distance horizontal of your vector, and B is going to be your y component of your vector, or the vertical distance of your vector. So let's look at 2 and -3, okay? Notice how they are denoting this. Vector u is equal to 2 comma -3. Notice that they're using these pointed parentheses, okay? So please don't mistake that for 2 comma -3. 2 comma -3 is a point. What exactly does 2 -3 with pointed parentheses like that look like? So come on over here and let me show you what that means. Let me erase this. So 2 -3 in this sense means the following. Let's write it down first. So if I gave you something like 2 comma -3 like that, I'm not asking you to go to 2 comma -3 like this. That's not a point. That is 2, -3, okay? 2, -3 written in that format means that the x component is a 2, like this. The -3 component means that from that ending value of 2, you went down 3 vertically. And so that is what they are giving you. And what they are asking you to find is the magnitude of that vector. Now, the vector, they named it was, if I'm not mistaken, was it a U? Hold on, let me go check really quick. Were we calling this vector U? Yes, we're calling it vector U. So back over here. So when I ask you, I'm telling you, hey, this is the components of my vector, 2, -3, and they're asking us to find the magnitude of vector U. That means I'm asking you to find how long is the vector U. Okay, they're asking you to find this length. How long is that vector? So I'm asking you to figure out the magnitude of vector U. Okay, so I know this is a 2, I know this is a -3, and I know already from earlier discussion that all I'm doing is doing Pythagorean theorem and then square rooting it. And in this case, I'm doing 4 plus 9 square rooted, which is going to give me the square root of 13. And I'm just going to merely stop right there, since that's not a perfect square. And I'm done. Okay? That's all you are doing. That is all that you're doing. So in this particular problem, the magnitude of vector U, is going to be the square root of 13. Okay? So no need to always keep drawing it and drawing it, drawing it, but drawing it out just kind of gives you perspective of what you are looking for. Okay? So let's do the drawing one more time. We have 5, 0. Let's come over here again, and let's erase here. And they're giving us U is going to be, vector U is equal to 5, 0. So that gives us information on how to draw this out, okay? So let's go draw this out. So 5, let's use green. 5, 0. So 5 is the horizontal distance. So here's my horizontal distance of 5. And then 0 is my vertical distance. So from right here, I'm either going up or down, but it said 0 actually. So I'm just going to undo that because I can't move up or down because it said don't do anything. So that's my vector. Like I'm done. 5, 0. So even just visually, I can tell, well, how long that green arrow? It's 5. There's nothing to do. But if we wanted to show our work and show that we can apply the formula, here we go. The, the magnitude of U is applied using the Pythagorean theorem. So 5 squared plus 0 squared is going to be the square root of 25, which is going to be 5. And then we're done. 5 is the magnitude of that green arrow. And visually, obviously, using our little eyeballs, we can see that it is 5 units long, right? That is really poor drawing eye. Okay, now, what happens then if we can use graphing all the time? Wow, hold on. If we can use graphing, it's easy to determine how long our vectors are going to be, our magnitude, but sometimes we get problems that are not easily going to be drawn out and be able to determine it by just looking at it. So let's do a problem that involves fractions and just do the arithmetic, right? So the magnitude of vector W, and by the way, if you've noticed, I've been drawing vectors either by drawing an arrow completed like that, or I can draw it like this, half an arrow. Those are both accepted ways of writing vectors, okay? So the magnitude of vector W is going to be the fraction 3/9 squared plus the other fraction 4/5 squared. And then I know I have to ultimately square root it. So let's do the math. Let's do it by hand. So 3 squared is 9, 9 squared is 81, 4 squared is 16, and 5 squared is 25. And you can, at this point, just use a calculator. Depending on your calculator, you could probably type the whole thing or just enter the inside of that radical and then simplify it. And if you do it step by step, the inside of this radical ends up being 169 over 225. And then the square root of that numerator is a 13, and the square root of that denominator, my bad, is 15. So in this particular problem, the length of our vector would be 13/15. Okay? So hopefully so far you're finding this quite easy. Let us go back to the previous page here and talk about, again, the component vector, which we just discussed anyhow. But what's going to happen sometimes is that there are going to be problems where I will give you the initial point and the terminal point. Let's call it P and Q. So pictorially, what I mean by that here, if I said I gave you P, P would be this piece right here, and I would give you the coordinates of P. And then this here, this point will be called Q, and I will give you the coordinates of Q, all right? So that's different. So let's say I asked you to find the components of PQ. If I'm asking you to find the components of PQ, what I'm asking you to find is what's in green. This is the X component, and this here is the Y component. That's what I'm actually asking you to find, okay? This is component X. Wow, hold on. Let me change my component X, and this is component Y. So here we go. Here is what's happening. They gave us an initial and a terminal point. My initial point, so write with me, initial PT point is P, and in looking at the picture, it's 2, 2, and my terminal point is Q, and it's -1, 4. All right, so that's my initial and terminal point, 2, 2, and -1, 4. So let's do some drawing over here. So back to this graph that we keep using. 2, 2, and -1, 4. So 2, 2, and -1, 4. And I'm going to draw this vector. So there's that vector that they gave us. And they're asking us to use 2, 2, and -1, 4 to figure out the components. All right. So this is what they're actually asking us to do. Graphically, what does that look like? So I'm going to click this here, and I am going to drag it back to the origin. Okay. Anytime I give you an X and Y of the endpoints of your vector, and I ask you to find the components, what you are actually doing is taking that vector and translating it back to the origin without changing its direction, okay? And when you do that, visually, we can easily see I'm going to change the color here to yellow. Visually, you can see what the x component is going to be and what the y component is going to be. Can you not? The components of this vector that you originally had is going to be negative. Oh my goodness, I keep forgetting to change my pen. Is going to be -3. I promise I can write -3, comma, and then the arrow's pointing 2 for the vertical. That's what we're looking for. That's your answer. Those are the components. Okay, again, -3 because this arrow went left, and up 2. It's like doing that rise over run stuff that you've done in the past, okay? That's basically what you're doing with vector components. So that's the answer. But how do we do this if we can't always just drag our arrows on our paper, right? How do we do this algebraically? Again, there's a formula for you to be able to do this. So remember this answer, and let me show you the formula. In order to find the components of your vectors given 2 points, all you have to do is do some subtraction. All right? And the subtraction says this. So let's do this. Vector v is equal to, right, the component vector parentheses there. Take the second x, and the second x is going to be the ending or the terminal point. So let me actually label this. X1 and Y1 is the initial, and X2, Y2 is second point you end up at. So take the second x, in our case it's a -1, minus the first x, which is a 2. Okay, so don't forget that this minus is part of your formula, comma, and then take the y2, 4, minus from the formula, and then the y1, in this case, is 2. And now we just do some simplification of our arithmetic. -1 minus 2 is -3, and 4 minus 2 is a 2. So there's your vector component. So there's no need, minimizing here, no need to move the graph. Remember, our graph was originally over here at 2, -2, right? And we moved it back to the origin so that we can visually see the components of vector. And yes, you can absolutely do the following. Here's my initial. Let's expand this here. You don't have to purposely go back to the origin, but I can do the x movement from here to here was, well, I went left 3 units, and then I went up 2 units. That's what I did, right? I went left 3 units, and I went up 2 units, okay? So yes, if you have a graph and a picture, you can easily tell me what the components are because you're just describing the x and y movement, okay? So that's how you find the components of your vector given 2 points, all right? And please remember here, order matters, okay? Order matters. You must always start. So if you would please write this in your notes, start with the terminal values. Always start with the terminal values, all right? Start with the arrow, all right? So over here, I want you to notice, I'm highlighting here. These are your terminal values because you're here by the arrow, okay? Start with -1, 4. There's my -1, and there's my 4, and then you subtract your initial values, all right? Let's wrap this up. Then we talk about adding and subtracting and multiplying vectors. All right. pretty straightforward. Adding means you're going to add the vectors in the corresponding spots. So what I mean by that, if I asked you to add the u vector plus the v vector, I need you to add the x with the x component. That's what that means. And the y component, that's what that means. Okay? Same thing with subtraction. Stick to the x components being put together and the y components being put together. If you talk about multiplication, you just take whatever that c value is, that constant, and multiply it by each one of the components. So let's do this. U plus v. Well, let's do some writing. My u vector component is 2 comma negative 3. And my v component is negative 1 comma 2. So we are going to make sure that we are adding the corresponding parts correctly. So the pink goes with the pink, and this green goes with this green. All right. 2 plus negative 1. 2 plus negative 1 is a 1. Negative 3 plus 2 is a negative 1. And you're done. Let us do u minus v. So let me rewrite these same problems. 2, negative 3 minus negative 1 comma 2. All right. You can distribute that negative first and then add, or we can just straight subtract right off the bat. So again, make sure you focus. The 2 is going with the negative 1, and the negative 3 is going to go with the positive 2. But this time we're subtracting, okay? So 2 minus negative 1. I'm going to actually write it out here this time. 2 minus negative 1, and then negative 3 minus 2, just to kind of put them together. So 2 minus negative 1 is 2 plus 1, and negative 3 minus 2 is a negative 5, okay? And the other way that I was going to say is that if you want to take off that negative, you can do this. 2 negative 3 minus negative 1 comma 2. You can change it into a positive. You can say, well, I want to make this into a positive, so that we have to distribute the negative. So this turns to a positive 1, and this turns to a negative 2. And so then you are adding 2 plus 1, that's a 3. And negative 3 plus negative 2 is a negative 5. Same thing. Okay? Next, multiplying. Negative 4 has to multiply by the vector u. And all you do here is distribute. Multiply, just like if it were parentheses. So you are just taking that vector and you're saying, hey, change the direction. Negative means it's going to flip on you, and distribute. So negative 4 times 2 is a negative 8. Negative 4 times 3 is a 12. We're done. So now pause the video, and I want you to try D on your own. And let's see if you can do all the operations together in one shot. All right, I'm going to talk this through real quick, and you can check your work. So let me set this up. Notice I'm consistently putting those pointy parentheses. I'm sure there's a actual word for it, and I should know it by now. All right, let's distribute. 2 times 2 is 4. 2 times negative 3 is negative 6. Let's put those parentheses back. Now I'm going to choose to multiply by negative 3. Okay, so I'm going to use that negative. And so because I'm choosing to multiply by negative 3, I'm going to have to put a plus here. Okay, because I used the negative. So negative 3 times negative 1 is a positive 3. Negative 3 times 2 is a negative 6. And because you just can't leave it blank. Understand? If you multiply by negative 3, you've got to put a placeholder, and that's my plus. 4 plus 3 is a 7, and then negative 6 plus negative 6 is a negative 12. Okay, so there are the 4 answers to these type of problems. And hopefully you are finding them pretty easy to understand. Those are the final answers. Let me box them in and make sure you have done the same. Now, pictorially, what does this mean? Like, what are we doing when we're doing these operations? So hang in with me just a moment more so that I explain what is happening here, okay? So let us use a simple example like A and show you exactly what is happening graphically. So again, let me erase all of this and let us show you graphically what does U plus V mean. Okay, so my U plus V was 2, -3. So let me see, 2, -3 plus, and the other one was -1. So I rewrite the problem, and we found out our answer was 1, -1. So here's what this means. So let's draw the first vector. Vector U is 2, -3. So the component was right 2, down 3. So I'm going to go right 2, and down 3. Well, actually, you know what? Hold on. Let me get my little arrow. So I'm going right 2, down 3, down 3. So that's about right here. Okay. That makes sense? And it didn't draw an arrow, so let us just put that arrow here. Okay, right 2, down 3. And the other one was -1, +2. So that means left 1, down, up 2. So left 1, up 2. So that means I'm going to go right here. That makes sense? You know what? Let me just draw this over. So 2, -3. All right. So what does this mean? What is happening is you are adding these vectors. And when you add vectors, you have to add them head to tail or tail to head. And what I mean by that is you have they have to have alternating head tail combinations. So I can either move this one right here, because right now they're both, their heads are attached to one another. I am going to either move that one to right here, right? And so now I have a head and tail matching, or I can move this one and put it right here, and I have a head and tail matching, okay? So whichever one you want to do, you can move, and you're going to end up noticing it's going to be the same answer. Here's what I want you to realize. So let's choose which one. Let's choose this big one, and let's move it over here. So if I'm adding, I'm just connecting them together, right? And what I'm asking you to find out is where, if it's connected together, did the final answer end up being? Well, if I start here at the origin and I went here and then I added this distance, where did I end up? I ended up right here. And what is that value? That value is the 1, -1 that you just told me was where it would end. Do you see what happened? And you're done. If you wanted to choose moving the other one, let's move the other one. I'm going to put this right here, back where it was. And let's move this one instead. Let's say you decided, no, I wanted to move this one head to tail. So here is my head to tail, right? There you go. And let's track this movement. So this time the origin's right here, and I went along here, and then I stopped, and then I went over here and stopped right here. There it is. I'm still at 1, -1. So that's what combining vectors means. It's asking you, well, where is the new vector when you added both of those together? The new vector ended up being this one. That's the new vector. So the two blues, when you added them, the U plus V result in the red. And the red here, goodness, I keep doing that red is the representative vector for u plus v. All right, that's it. That's your introduction to vectors. Hope it seems pretty easy. Thanks for watching.